Hey, here we go. Part two of chapter one, How Geographers Look at the World, is called Map Projections and Scales. Here we go. Okay, so cartography is the science of map making. At first glance or thought, guys, stop talking. Just said that. Go ahead and take notes on this. Go ahead. You can turn those in after. Cartography is the science of making maps. After our last little, I guess, assignment, you could tell that's not as easy as you first might have thought it is, and that's just because we're taking a 3D object and we're making it into a flat piece of paper, a 2D object. And when you do that, you start getting distorted. Okay? This guy, he's going to cut up a beach ball and try and do what you guys did. We're not going to watch this video, but I'll let it play. You'll see him stabbing that beach ball, and then he'll cut it up, and then he'll kind of do what you guys did with the paper, try and stretch some of the angles, and oceans get all messed up. And of course, he's not thinking of latitude and longitude and size and shape, but that's kind of what cartography is. Okay, these are the things that actually gets distorted. Shape, area, distance, and direction. We call it SAD because it's sad. There's a couple different types of projections or categories of projections. You have cylindrical, conic, and azimuthal. Okay, and the main problem, like I mentioned before, is Earth is round, maps are flat. Cartographers run into issues when they have to deal with that kind of stuff. Okay? All right. Okay, our Mercator, or Mercator, is probably our most popular map. This is the thing that's in our cell phones. This is our GPS map. This is the one our Google Maps and Apple Maps use because the lines of latitude and longitude are true. They maintained latitude and longitude without being distorted. The problem with the Mercator is that the size of our continents is off. So this is Greenland up here. This is Africa. And in real life, Africa is about 8 times as big as Greenland. Same thing with Antarctica and South America. So the size of our continents in the Mercator is wrong. So you have latitude and longitude are correct angles, which is a strength. A disadvantage or a distortion is the size of our continents. The main purpose for our Mercator is navigation. Okay. All right, the Gall-Peters projection. This one's strength is the landmass. Okay, how big each continent is. So that is correct. In Greenland, now you see Greenland and South Africa. And you could see how South Africa is now way bigger than Greenland. The problem here is that the shapes of our continents are now inaccurate, especially near the South Pole, Antarctica, and the Arctic, the North Pole. Okay? So of the Gall-Peters, you have strength is the size is correct now on our land masses. The distortion is that the shapes are off. Size is right, shapes are off. So these are all kind of maps we've probably seen 100 times, and we just never thought, man, that is messed up. All right, here we go. We're not going to watch that. This is a projection or an overlay of the two types of maps. You can see the differences. That's Africa in the Mercator. That's Africa in the Gall-Peters. So the shape is off. The size is different. This is the same Earth we know. Okay, the Robinson map projection. I remember Robinson map projection because of the round edges. There's other types of map projections, but we're not going to talk about those. So all you need to know is this round curved edge is our Robinson. Okay. Now, the problem with the Robinson map projection is that our North and South Pole are not really flat. So that's an issue with this one. So it has the curved lines. Another problem is near the poles, the lines of longitude are distorted because it kind of curves in, and all our lines of longitude are parallel to each other. All our lines of latitude are parallel to each other in real life. In these projections, especially this one right here, they're not. They get curved, okay? The good thing about the Robinson map, so good and bad about Robinson, main thing is it's distorted all over the place. Size, shape, latitude, longitude. The good thing about it is that it's distorted at a smaller rate than the Gal-Peters in size or shape. So it's kind of your medium. It's a really popular one that people use, but it just kind of depends on what you want. If you want land mass, you're going to go with the Gal-Peters. If you want shape, you're going to go with the Mercator, or navigation, you're going to go with the Mercator. If you kind of want a happy median, you'll go with the Robinson, where it has a little bit of everything, but not correct in all places. Okay. Okay, here's the azimuthal. This is the northern hemisphere right here, so this is a bird's eye view. This is looking down on Earth. This is the North Pole. This is good when we're talking about the Arctic or the Antarctic. Okay, so we're looking down on Earth right now. That's the Arctic. What's not good about it is the further you get away from the Arctic, the more distorted it gets. Okay, so most our maps are really distorted at the North and South Pole, the Arctic and the Antarctic, but the azimuthal is actually the opposite. So it's pretty accurate at the North or South Pole when we're looking at it like this, and then it gets distorted as you go away. And again, the issue is that you're taking a 3D object and you're making it 2D. Now, we probably won't notice it at all. We'll never know, but cartographers deal with that. All right. Okay. This is the orange pill. This is Good's interrupted projection. So if you drew the 7 continents on a orange and then you unpeeled it and squished it flat, that's kind of what you would get. The problem here is that Greenland is on there twice, because that's the part that got ripped in half, and then parts of Asia are also on there twice. It's pretty accurate. The problem is that it's interrupted. So the oceans are all taken apart. It's not aesthetic. So, I mean, if I had that on my wall, I mean, I think it'd look pretty cool, but, you know, it's just not filled in. The Mercator, or the Mercator, is actually a Good's interrupted. They just spread it out so that it looked like a complete rectangle. Okay? They filled in those places, or kind of stretched it like if you had a picture on a PowerPoint and you clicked and dragged one corner. And that's kind of why the Mercator is distorted at the poles, or the Greenland looked bigger, because they had to stretch Greenland, and that's why it was bigger. It's actually just like Good's interrupted, just not stretched. Okay. All right. Okay. We kind of talked about this last time. My biggest issue last year, so I'm going to do with my students, was they got confused with this, so I'm going to do a really good job of explaining this year. Okay. Our lines of latitude run east to west, and they're all parallel. So you have 0, 30, 60, and then 90 up here at the poles. And of course you have other lines, but they're all parallel to each other. Okay. Now our lines of latitude actually measure north and south. They run like this, but they measure north and south. So they're kind of like steps. So it's like, let's say first step, second step, third step, fourth step. So if I said, where is my puppy? He's on the third step. 1, 2, 3. Okay. He's at 90 degrees north. You see how that works? So I'm measuring north and south with my lines of latitude because they run east and west. That's going to be a question you'll see about 100 times. What do your lines of latitude measure? And you're going to say, lines of latitude, okay, east to west. Oh, they must measure east to west. No, they measure north to south. Okay. This is our equator. It separates our northern hemisphere from our southern hemisphere. Okay? Northern, southern. It's very hot and humid around our equator. There's a lot of tropic climate. All right. This is our lines of longitude. Our middle or our equator of longitude is called our prime meridian. So that's our 0. That's our prime meridian. And just like latitude measures north and south, longitude measures east and west. So we go 0, 30, 60, 90. So now we're going sideways. This is our 30 degrees west, 60 degrees west, 90 degrees west. And you'll always have this on the map. You just have to know, if I'm looking for west or east, I'm using my lines of longitude. You have to know that. Longitude runs north and south, measures east and west. Okay. Okay. You don't need that. Okay, our international date line. Calm down, Austin. That's not where you go to get a date. Oh, yeah. Got one laugh again. It's one more than yesterday. Anyways, this is the day or the place. Like you're traveling to, let's say you're traveling on I-10 from Austin to El Paso, and you pass through the mountains right there by Van Horn, and all of a sudden you look at your phone and it's an hour behind. That's the same thing this is. It's just the date, our date line. So nothing actually changes. You don't go back in time. It's just a date kind of thing. Okay? Okay, our cartographic scale, you guys got a little bit of a sample of this when we did our state of confusion assignment. It's something like 1 inch equals 1,000 miles. Obviously, we can't have a map that 1,000 miles is 1,000 miles. So we have our maps, and they're 12 inches by 10 inches, and 6 inches equals, I don't know, 1,000,000 miles or something. So that's our cartographic scale. It communicates to you how much is actually really on that map. Okay. Now we also have geographic scale. So if I said there's a global scale, this is a global scale map, I'm probably talking about all of Earth, just like the world maps we've been looking at. If I said regional or national, I'm probably talking about a map of Texas, or a map of California, or a map of the United States. If I said a local scale map, I'm talking about Williamson County. I'm talking about Travis County. I'm talking about Lake Travis ISD, BK, Lakeway, Austin. That's a local scale. Okay, here we go. Okay, data scale. This is important because of perception. Okay, so if I told you, hey, 1 million people live in Australia, or let's say 10 million people, okay? 10 million people live in Australia, and that's Australia. And you'd say, well, it's kind of densely populated. Not really, though, okay? Well, that's not the case for Victoria, Australia down here, because they're really dark. That means like 9 million out of those 10 million live in Victoria, and no one lives in Western Australia. But we have to talk about data scale because in these two maps, it doesn't tell you the whole picture when you just look at this and say, yeah, people live there, they're kind of all spread out. No, they're actually here, so you have to put that into perspective, okay? So that really comes into play when we look at maps like this one, okay? Let's look at this United States map, and we said, okay, this is cancer, patients with cancer by state. You'd say, wow, not a lot of people over here in the Four Corners, or there's a lot of people in Nevada, kind of in California. Wow, there's really a lot of people in Louisiana. And then you actually look at one of Louisiana, and there's some that aren't, okay? So it's not all of Louisiana, just most of Louisiana. There's a couple counties in there that, don't have high rates of cancer. This is big when we get close to election time and we start looking at, okay, Texas is a Republican state, and then you look at a map of Texas, and then you have like Austin. Most of Austin is Democrat, or El Paso, or a lot of the Valley, or Houston, but most of Texas is Republican. We just have some counties that are Democrat. So it's not always the case to say all of Texas is Republican. Okay, and that is it for